Alright, now we're moving on to the last bit of the motion stuff, which is, it's going to take a few lessons to get through. Alright, it's pretty funky stuff. Special relativity. Einstein involved in that. So, first of all, before we get into some of the real weird funky stuff, we need to look at frames of reference. So it basically, frames of reference means how you observe something, or something observed depends on whoever's observing it and what's going on between them, etc. So there's some videos on the web page links that are well and truly worth looking at. All right, we talk about Einstein's relativity and the frames of reference one. Now, the 1960s video is a bit of a laugh, but also demonstrates the idea of frames of reference very well. All right. Now, another thing that you need to keep in mind is what's called Gedanken. Now, Gedanken is a German word, and what it actually means is thought experiment. Alright, so Einstein used these thought experiments when he was thinking about this sort of stuff. So, for examples, if you're in a train here, and there's a train, there it is, and it's going this way at 60 kilometres per hour, and if you're on the train and you're running, say this way, at 5 kilometres per hour, then me, who's standing out here, looking at you, is going to observe a very different thing to your friend in the train looking at you. Because your friend and myself have very different frames of reference. Your friend is actually moving with you and the train, whereas me, I'm still on the ground. So me, what do I see you as? Well, I see you as coming towards me at 60 plus the 65 kilometres per hour. Your friend, however, because they're in a different frame of reference to me, and their frame of reference is moving at 60 kilometres per hour, they only actually see you coming towards them at 5 kilometres per hour. Alright, so when we're talking about frames of reference, it depends on what the observer is doing. So then that example there is, I've expanded a bit on there here from what it is in your notes. So it depends on what the frame of reference. My frame of reference is stationary. Oops, this is me here. My frame of reference is stationary in terms of the Earth, stationary. But your friend actually, that's my consideration, but your friend actually considers that their frame of reference is stationary, and then they're not moving at 60 kilometres per hour, but I am. That's a whole bunch of other stuff. But their frame of reference, because they're in the same frame as what you are, the train that's moving at 60, they only see you at 5. So it depends on what relative to what. So in terms of this, the velocity of A relative to B, so if you are A and I am B, then the velocity of A relative to B so U relative to me, and we write that as VAB, would be the velocity of A minus the velocity of B. Now when we go back here, you are moving, as far as I'm concerned, at 65, so we're kilometres per hour, and I'm moving at 0, so 65 minus 0 is 65. Your friend, however, is if they were B, sorry, U relative to your friend is the velocity of U, 65, minus the velocity of your friend, which is 60, which is the 5. All right. So it can be a little bit tricky. So the velocity of A relative to B is the velocity of A. So here is, let's get rid of that. So here is A, and A is moving VA. And then you've got B here, and B is moving VB. And it's velocity of A minus velocity of B. Alright, so let's have a look at a couple of examples then. Right, the first example, and then I'll do another theory. So which of the following statements is the best statement about inertial frames of reference? Now, I didn't say about inertial, but inertial means not accelerating. Alright, so it's not accelerating. That doesn't mean it can't be moving, but it must not be accelerating. So if it's moving, it must have a constant speed. So which one of the following statements is the best statement about inertial frames of reference? So frames of reference must be stationary. Well, they don't have to be, so maybe that one's not. It's just inertial frames of reference must be accelerating. Well, that's definitely incorrect because they can't be. The laws of physics have the same form in all inertial frames. Inertial frames cannot be moving at the speed of light. Well, or close to the speed of light. Well, over here I said yes, they can be. So that one's out. So the best statement, because this is must, we'll cross that out. The best statement is in fact this one here, that the laws of physics have the same form in all inertial frames. And so that's when I didn't mention the definition of that. So inertial frames, oops, that's terrible. Inertial frames of reference. The laws of physics hold. Alright. Alright, so let's have a look at another bit in your notes there. So that's this diagram. Alright, so it's this diagram here. It says if you threw a ball while standing on the back of a truck, you've got to take into account the speed of the truck and also yourself. So we're talking about someone who's standing still here on the roadside, and what does that person actually see standing still here on the roadside. So over here we've got our ball truck moving forwards, so that's our truck moving that way to the left, and I'm going to call that, so that's forwards. Then we've got our ball moving the other way, backwards. So what does this person standing here, what do they actually observe the ball doing? Right, so what do they observe the ball doing? So in terms of the ball, what do they see? Well, because what they actually see is we need to add these velocities together. So what they actually see is 40 forwards plus 10 backwards. Right, so the forwards relates to the truck moving forwards, and the 10 from the ball's been thrown backwards in relation to the truck. Now, because that's the opposite direction, we could say that's minus 10 forwards. So the total, what this observer will see is the ball moving 30 metres per second forwards, which actually means they're going to see the ball not moving towards them, but moving away from them at 30 metres per second, the truck moving away from them at 40 metres per second. All right. So, as it says in your notes, the ball moves slower than the truck in the same direction of the truck. So that's the frame of reference. So that's me. However, if we change the frame of reference to the person standing on top of the truck, the person standing on top of the truck has a different perspective altogether. So that person on top of the truck sees the ball moving away from them at 10 metres per second. So both people are correct. All right, so the blue person seeing it at 40, the red person seeing it at going 10 backwards. Both of those people are correct, and the reason for the difference is the frame of reference. So their frame of reference is different. Right, where they are looking at the thing is different. All right, so let's have a look at another example. This is another. All right, another exam question. A bushwalker stranded while walking, search and rescue, drop a parcel from the helicopter to the book. They drop the package, so here's the package here. They drop the package at a height of h directly above the bushwalker. Helicopter is moving with a velocity of 10 metres per second, angle of 30 to the horizontal, as shown below. The package lands on the ground 3 seconds after its release. All right, so here is our 10 metres per second. Now remember, if they're moving in that direction, there's actually two components. So there's a horizontal component and a vertical component. So the package is going to have both of those. So as the path shows, when it's released, it's going to go up a bit and then forward. So, assuming the helicopter continues to fly with its initial velocity, where is it when the package lands? Okay, so where is it when the package lands? It meaning the helicopter, okay? So we've got to think about what's going on with the helicopter and what's going on with the package. So if we split it up as vertical and horizontal, and as we've seen before in projectiles, in the horizontal direction, and remember we're inertial frames of reference here, so all laws hold. So in the horizontal direction, the package, neglecting air resistance, which it says here, ignore air resistance. So our horizontal component doesn't change. Not only doesn't it change, it's the same for the helicopter and the package. And so they were both moving at exactly the same in the horizontal direction. So after 3 seconds, and as we know, V equals x on t, so x is vt. Velocity horizontally is the same for both of them. The time is the same for both, which is 3 seconds. So the distance they move horizontally will be the same. And if that is the case, then A, it is directly above the package. So when the package goes bang, bang, bang down here, the helicopter is actually now up there in that time. Well, it may be higher than that in altitude, maybe up there somewhere, but horizontally it's in the same place. All right, so in your notes there's a few questions in your notes here about this in frames of reference, so you should do those now. Again, as always, if there's stuff you need clarified, make sure you ask. There's also on the website my notes and those some video links as well.